Hi everybody, welcome back. So in class today we did an investigation to introduce the idea of representing the solutions to a differential equation visually, and we call that visualization a slope field. Today what we're going to do in this video is go through sort of the nitty-gritty of drawing a slope field and making sure that we understand how to do that, as well as using slope fields to help us answer questions about differential equations. So let's start with this. If I ask you to solve the following differential equation and list 5 possible solutions, here's what that would be asking you to do. So the first thing is I would want to separate my dy and my dx so that all the x's are on one side and all the y's are on the other side. So I'm going to multiply by dx on both sides. I'm going to have dy equals negative sine of x dx. Then I'm going to use an integral to do the antiderivative on both sides. And the antiderivative here would have an invisible 1. Well, the function here would have an invisible 1, so the antiderivative would be y. The antiderivative of negative sine would be cosine of x plus c. Now, we only put the plus c on the right side, so we can use this as a general template for writing down possible solutions. Because c is not pinned down, it could have multiple values depending on whether we have an initial condition or not. 5 possible solutions could be y equals cosine of x plus 1, y equals cosine of x minus 1. We could even get a little crazy and make it y equals cosine of x plus 1.5, or y equals cosine of x minus 100. That c value can change, and it could be determined by our initial value, but we don't have that here, so it could really be any constant. We could also do y equals cosine of x, just as to have a fifth example, plus 1.75. That's just 5 possible answers. So the big idea of today is, how can we represent all of those solutions without making a list? Because really, we listed 5 answers here. We could have listed infinity answers. You could make that last constant whatever you wanted it to be. So if we want to represent this without having to make a very long list, one way to do that is to visualize the solutions without solving the actual differential equation or making a very long list of possible solutions. Here's what a slope field does. Since a differential equation tells us slope values, we can use that differential equation to picture little tiny pieces of the graph at those numbers. For example, let's start by making a slope field on this graph. Our differential equation is the same one we just solved. And since this side of the equation only has an x, the slope only depends on x. So on this graph, I'm not going to worry for each of these dots about the y value of the ordered pair that I'm drawing on. Only going to worry about the x value because the slope only depends on x. So let's make a list of some slopes that we can know. When the x in our chart is negative 2 pi, dy over dx will be negative sine of 2 pi. Now, sine of 2 pi is 0. So it would be 0. So in this entire column, where all the x values of those little dots is negative 2 pi, I'm going to draw a slope of 0, which looks like a horizontal line. Now let's see what happens at negative 3 pi over 2. Well, if I take this and I substitute it into here, sine of negative 3 pi over 2 would be positive 1. Negative sine would be negative 1. So all of my slopes on this column will all be negative 1. Now it doesn't matter how exact your slope little lines are, as long as it's going downhill, it'll still help you get that picture. Next, we're going to look at what happens at negative pi. Now, if I take negative pi and I substitute it into here, sine of negative pi would be 0. So that's going to give me a flat little piece of slope. Then I'm going to take negative pi over 2. At negative pi over 2, sine would normally be negative 1, but since this is negative sine, I would have positive 1. So now my slope's going to go uphill. Next, I'm going to look at 0. So sine of 0 is 0, which means all the slopes on the y-axis are all going to be flat little horizontal lines. They all have a slope of 0. At pi over 2, positive, sine is positive 1, but since we have negative sine, it would be negative 1. So it would look like this. Little negative lines. At pi, sine would normally be 0, and negative would make it still 0. At 3 pi over 2, my slope is going to be, normally sine of 3 pi over 2 would be negative 1, but since it's negative sine, it would be positive 1. So I'm going to draw little uphill slopes. And at 2 pi, last but not least, at 2 pi, sine would normally be 0. Negative doesn't change that. So this is what we call a slope field. Now we're going to try the second part of the question, which says, then draw the graph of the solution that passes through the point 0, 3. So let's find the point 0, 3. On this graph, the point 0, 3 would be located right here. So we want to draw the particular solution that's going to go through that point. What I'm going to do is treat this like a wind tunnel that sort of shows me the direction. I don't have to follow any of these lines exactly. I just have to follow the direction. So at 0, 3, it's kind of flat. So I'm going to go kind of flat, and then the slopes go downhill, and then they flatten out, and then they go uphill, and then they flatten out, and then they go downhill, I'm assuming. And then backwards, they go downhill, and they flatten out, and then they go uphill, and then they flatten out. Now, if I look at that picture, let's talk about how that helps me visualize this. I know from my previous problem that the original function here would have been cosine. If we look at the graph we just drew, this looks like a cosine graph with the initial value 3. So what this does is it allows me to show that all of the solutions to this differential equation have something in common. They're all cosine graphs that are just shifted up and down. I can visualize this by looking at the wind pattern and the slope field, and it helps me see that all these graphs are the same thing, just shifted into different places. Then I can pin down that exact function by drawing a graph on top of there that goes through an initial value. So let's see what we could use these for. Here are a couple examples of application questions and follow-up questions that come after you draw the slope field. So this one says, graph the following slope fields for the given points. Now you'll notice that this differential equation, because there's an x and a y here in the equation, the slope depends on both x and y. So let's see how that changes how we actually graph this. Because our other slope on this page only depended on the x, I only needed the x value of the ordered pair that I was looking at. So I only looked at the x-axis. Since this one depends on x and y, we're going to need to have the x and the y value of our ordered pair and use both of those to figure out dy over dx. So let's start with our first ordered pair. This first ordered pair up here has an x of -2 and a y of +2. Now if I plug those numbers in, I'm going to have negative, the x is -2 and the y is +2, which gives me +1. So I'm going to draw a little tiny slope going uphill. The next ordered pair I'm going to look at is going to be this guy right here. He has an x that's -2 and a y that's +1. So I'm going to have -2 divided by 1, which is 2. Now if I compare these two answers, a slope of +1 is going to be flatter than a slope of 2. In other words, a slope of 2 is going to be steeper. Even though it technically is good enough to just make it go uphill, you want to make these as accurate of slopes as they can be. So you want that orange line to be a little bit steeper than the red line. Now let's look at the point -2, 0. So if I plug those in, I have -2 over 0, and that gives me an undefined answer. Now you'll also notice that that particular spot on the graph didn't have a dot on it. In other words, I did that problem, but I didn't really need to. I wasn't required to by the problem. So, in a few minutes, we're going to kind of answer the question, why do you think the problem didn't actually require me to graph a slope there? Next, we're going to do the point -2, -1. So I'm going to have -2 divided by -1, which is -2 divided by -1 is +2, and then I make it negative. So it's going to be downhill like that. Next, I'm going to do the ordered pair -2, -2. So it's going to look like this when I substitute those into my equation. This is +1, make it negative. Basically, this part and this part are like mirror images of each other. They're flipped over. Now let's do the next column. Now I'm not going to write it all out. I'm going to imagine plugging them into here. So if my x is -1 and my y is +2, that's going to give me +1 over 2. So it's going to be a little bit flatter. If my x is -1 and my y is +1, that's going to give me +1 divided by 1, which is +1. If my x is -1 and my y is -1, I'm going to have +1 divided by -1, which is -1. If my x is -1 and my y is -2, I'm going to get -1/2. Again, these are mirror images of each other, so that's a neat pattern. Now if my x is 0, in other words, this point, this point, this point, and this point, all my x's are zeros. If the numerator of this fraction is a 0, that guarantees all the answers will be zeros regardless of the y. So I'm going to use that fact to graph little horizontal lines pretty quickly there because I know that they're all going to be zeros. If my x is +1, then I'm going to have -1 divided by 2, which is -2. Oh, sorry, is -1/2. That was my bad. If I have -1 divided by 1, I'm going to have -1. If I'm going to have -1 divided by -1, I'm going to have +1. And if I have -1 divided by -2, I'm going to have +1/2. Then all my numerators are going to be -2. So -2 divided by +2 is -1. -2 divided by 1 is -2. -2 divided by -1 is +2. -2 divided by -2 is +1. Now this is a tedious process. I would definitely take it slow and double check ourselves. And one of the things I would highly recommend that you do is at the end stop and make sure it looks like it makes sense. There should be a picture that makes sense. If you notice one of your little slopes is going the wrong direction, fix it. Now for part A here, why do you think you were not asked to graph the slope field on the x-axis? Well, let's look at what happened when we tried to pick a point that's on the x-axis. When we tried to pick the point -2, 0, what we noticed was that our slope ended up being undefined. So we were not asked to graph the points there, because how do you graph an undefined slope? So all the slopes on the x-axis would be undefined because all the x coordinates, y coordinates would be 0, and you can't divide by 0. Now, I want to point that out to you because one common mistake that we see when we're working on these problems in preparation for the AP test is that students graph these wrong since they put extra pieces of information in. For example, some students try to graph slopes where there shouldn't be slopes. The problems will give you specific dots on the ordered pairs where you need to draw a little slope picture, so it's really important that you only graph the slopes on those specific dots. Part B, do you notice any patterns? Well, I noticed for me, for example, that the above, that marker is the worst. Just kidding. Let's try another one. Above the x-axis is just the reflection, I'm going to draw a little squiggle, of the below the x-axis. Now, it doesn't always work that way, but there are always patterns to look for, and that's an example of one of those patterns. I also noticed that to the right of the y-axis is just a reflection of what's on the left. I also noticed that this diagonal, if you follow this diagonal line, all of those slopes are +1. Same thing on this diagonal. All of those slopes are -1. I also noticed that all dy dx on the y-axis are equal to 0 because all the x coordinates of those ordered pairs are 0. So you should be able to stop, and they're never going to ask you about patterns on the AP test or on our test, but this is to help you stop and think that this makes sense. Last but not least, in this question, we are going to ask you to sketch the specific solution that passes through the point 0, 1. Now the point 0, 1 is right here. Now the specific solution to me seems to go like this, and then I run into a place where my slope is undefined, so I'm going to stop. And then like this, and then I run into a place where my slope is undefined, so I'm going to stop. I wouldn't keep going through that axis because I know that all along this axis the slopes were undefined, so I would stop there. Next, let's look at this example. So let's first start by graphing a slope field. So I'm going to pick all the points where x is -1. Now in this column of the graph, all the points have an x coordinate of -1. And then what I'm going to do here is show you, instead of going point by point, how to use patterns to make these graphs. In all the places where x is -1, -1 to the 4th, which is the first thing I would do to plug that in, would just be 1. So all of the slopes in this column are just going to be the y value -2. So the y value here is 3. 3 minus 2 is 1. The slope is 1. The y value here is 2. 2 minus 2 is 0. The slope is 0. The y value here is 1. 1 minus 2 is -1. The slope is -1. The y value here is 0. 1 times -2 is -2. Now I'm going to look for what happens when the x is 0. So in this column, I'm going to do 0 to the 4th times y minus 2. 0 to the 4th is 0, and 0 times y minus 2 is going to give you 0 every time. So in this column, all the slopes are 0. In the last column, all the y values are positive 1. Now positive 1 to the 4th times y minus 2 would just be y minus 2. So again, in this column, all the slopes are going to be the places where y, like we're going to take the y value and subtract 2. So 3 minus 2 is positive 1. 2 minus 2 is 0. 1 minus 2 is negative 1. And 0 minus 2 is negative 2. And that's what my slope field looks like. Now, part A here doesn't say the same type of question that we saw in problem number 1. What it says is describe all the points in the xy plane for which the slopes are negative. So how would you do that? In math, when the problem says that it wants you to describe, it means that mathematically. I know in other classes when it says to describe, that usually means to write a paragraph or an essay explaining what you're thinking. Here, it literally means using numbers and equations. So I want to find all the places where the slopes are negative. As soon as you see that word slope, you should think to yourself, hey, I've got dy dx, and dy dx tells me about slopes because derivatives are slopes. So to set this up, I would start mathematically by saying dy dx equals x to the 4th times y minus 2. And I want to find the places where this is negative. It's going to be negative when I'm less than 0. Now to solve this, we need to think about this as two different factors. We can agree that x to the 4th is always positive or 0. For example, if x was 0, x to the 4th would be 0. But other than that, something to the 4th power is always positive. So there's no way that this factor will ever be negative. Which means the only way to make this product, a number times another number, into a negative answer is that this part of the product must be negative. So we would write y minus 2 has to be less than 0, which is solvable because we have one equation now. So our slopes are going to be negative when y is less than 2. But now let's go back to the graph and make sure that that makes sense. Right here is the place where y is less than 2. And if I look at this picture, not all of these slopes are negative. As a matter of fact, some of them are flat. They're zeros. So saying that y is less than 2 is not enough. Remember how we said that this could have been a 0 if x was 0? Well, we want to make sure that that doesn't happen. If we're looking for just the negative slopes, we don't want this to be 0. So we would say y has to be less than 2 and x cannot equal 0 if we want to guarantee that we have a negative slope. Other than that, we're guaranteed to have a negative slope on our graph. We're going to go ahead and stop this today. We will practice this in depth over the next few days in class. Thank you so much for watching and have a great day.